In this video, I'm going to talk about some properties of the incenter of a triangle, and we are going to look at how to prove these properties. The first property that we're going to look at is that the three angle bisectors of the triangle intersect at a single point, which is called the incenter. Two angle bisectors will of course intersect at a point, but we will also prove that the third angle bisector will also pass through the same point. The next property that we want to prove is that the incenter is equidistant from all the sides of the triangle. In other words, the perpendicular distance from the incenter to the three sides is identical. The third property of the incenter is that a circle can be drawn with incenter as the center. This circle is called the incircle. In this example, the incircle is shown in purple. The incircle touches all three sides and is completely inside the triangle. The fourth property we're going to prove is the formula for the coordinates of the incenter, given by this formula highlighted here. Here x1, y1 is the coordinate of A, x2, y2 of B, etc. A, B and C are the three side lengths of the triangle. A is the length of the side which is opposite to vertex A, and similarly B and C are lengths of the sides opposite vertices B and C respectively. So let's see how to prove these properties of the incenter. Let's start by proving the first three properties. They all relate to the existence of the incenter. So in this triangle ABC, I have drawn two angle bisectors, the bisector for angle A and the bisector for angle B, and these intersect at point I. Next, I'm going to draw the perpendicular distances from I to the three sides. The first property that I'm going to prove is that all these distances are equal. To prove this, let's start by focusing on these two highlighted triangles, triangle AFI and triangle AEI. We're going to prove that these two triangles are congruent. As we can see, since AI is an angle bisector, these two marked angles are equal. Also, both of these are right angle triangles. Angle AFI and angle AEI are both right angles. So two angles of the triangles are identical. This implies that the third angle here must be identical because it's just 90 minus the smaller angle here. So for the highlighted triangles, all three angles are identical. Now if we look at this side here, AI, it's a shared side, which means we have a case where there's an angle, side and angle which is identical between the two triangles. In other words, the triangles satisfy the ASA condition and the triangles are congruent. Since the triangles are congruent, these two lengths are identical. We can call them both D. So we have proven that the distance from I to side AB is the same as the distance from I to side AC. Now the exact same argument applies for the other angle bisector, BI, and these smaller triangles. So by the same argument, side IF is the same length as side ID, because again the triangles are congruent. So we can mark the third side also as D. So we have been able to prove the property that the intersection of any two angle bisectors, point I, is equidistant from the three sides of the triangle. Now since the three distances are identical, we can draw a circle centered at point I with radius D, which passes through the 3 points of intersection of the perpendiculars and the three sides. Let's prove that the incircle lies completely inside the triangle. D is the shortest distance from I to AC, which means if we take any other point on the segment AC, that distance will be larger than D. So what that means is, because each point on the circle is distant D from I, it has to curve inwards away from side AC, and it will never intersect any other point on line AC. Similarly, for the other sides, the circle has to curve inwards away from each of the sides. What that means is that the incircle is bounded completely by the three sides of the triangle. So the incircle lies completely inside the triangle. So far we have proven these properties with the incenter defined as the intersection of two of the angle bisectors. Let's also prove that the third angle bisector also has to pass through I. To do that, I'm going to connect I to C with this dotted line. What we're going to prove is that this line IC bisects the angle C. To prove that, let's look at these two highlighted triangles. So for these triangles, as we can see, we have already proved that these two sides are both of length D. Also, they have a shared side, which is the hypotenuse of the triangle. Let me call that H. What that means is the length of the third side is also determined. It has to be h square minus d square for both triangles. So we have a case where all three sides of the triangle are identical. This again implies that the two triangles are congruent by the SSS congruency rule. And since the triangles are congruent, it means these angles have to be the same. So what we have proved is that IC is an angle bisector of angle C. Therefore, all three angle bisectors must intersect. Next, we are going to find the formula for the coordinates of the incenter. To find the formula for the coordinates, first we need to prove the angle bisector theorem. For the triangle ABC shown here, AX is an angle bisector. X lies on the line segment BC. A is the length of side BC, which is opposite vertex A. Similarly, B and C are the lengths of the sides opposite vertices B and C. The angle bisector theorem states that the ratio of segments BX to XC is C over B. Here C is next to BX and B is next to XC. To prove this theorem, let's consider any point on the angle bisector. I'm going to draw the perpendicular distance from this point on AX to the two sides. As we saw before, the two highlighted triangles will be congruent. To recap, the two triangles here satisfy the ASA congruency criterion. Here I have highlighted the corresponding angle, side and angle that are equal in the two triangles. Now, since the triangles are congruent, these two sides have the same length. Again, this argument can be made for any point on the angle bisector AX. So in this case, if we look at point X and the highlighted triangles, the exact same argument applies. The two highlighted sides are equal in length, so I can mark both of them as length D. Now let's look at the highlighted triangle ABX. The area of triangle ABX can be calculated as half times base times height. Here, if we assume that AB is the base, the height will be D, so the area is half times D times length of AB, which is C. Again, D is the height and C is the base length, assuming AB is the base. But the area of the triangle can also be calculated using BX as the base. I've drawn the height from A to segment BC and designated it as H. The area of the triangle can also be written as half times H times length of BX. In this case, BX is used as the base of the triangle and H is the height of the triangle. So cancelling out the common terms from this equation, we get D times C is H times BX. Now if you look at the other highlighted triangle, triangle ACX, its area can be written as half times D times B, where D is the height and B is the base. And again, if we assume that XC is the base, the area can also be written as half times H times length of XC. Again, cancelling out the common terms, D times B is equal to H times XC. So now we have these two equations. If we divide the left hand sides and the right hand sides, we get D times C divided by D times B is H times BX divided by H times XC. And then cancelling out the common terms, we are left with C divided by B is BX divided by XC. So we have been able to prove the angle bisector theorem. Ratio of BX divided by XC is C over B, and this will obviously apply to any other angle bisector of the triangle as well. In the following sections, we'll use this result to find the coordinates of the incenter. The next step is to derive something called the section formula. This will also be needed for finding the coordinates of the incenter. So here we have a line segment AB with endpoints x1, y1, x2, y2. We want to find the coordinates of a point P on AB such that the ratio of AP to BP is A to B. Since the ratio is A to B, I have marked AP to be of length AL and BP to be of length BL, where L is just some multiplier. The idea is that this makes the ratio A to B, where L could be anything. So let's start by drawing these horizontal and vertical lines as shown. The horizontal line is parallel to the x-axis and the vertical line is parallel to the y-axis. We'll start off by finding the x-coordinate of P, and the y-coordinate will have a similar form. So the x-coordinate of P is the same as the x-coordinate of M because they are both on the same vertical line. We already know the x-coordinate of A, which is x1. If we add the length of AM to x1, we get the x-coordinate of P. So to find xp, it's enough to find the length of AM. Let's look at this highlighted triangle ABN and compare it to the smaller triangle in blue, which is APM. These two triangles are similar because they each have a right angle and a shared angle at A. Now for similar triangles, we know that the lengths of corresponding sides have to be in the same ratio. So in this case, the ratio of AM to AN is the same as the ratio of AP to AB. The length of AP is AL and the length of AB is AL plus BL. And if we take the ratio, L cancels out and we are left with A divided by A plus B. Also, AN is a known length. The coordinates of N are x2 and y1. So we can determine the length of AN, which is x2 minus x1. So putting those two equations together, the length of AM is A times x2 minus x1 divided by A plus B. So we have found a formula for AM. Now all we need to do is pick these two equations and substitute AM in the first equation. If we do that, we get this formula. If we simplify this and cancel out the corresponding positive and negative terms, we get the formula xp is b times x1 plus a times x2 divided by a plus b. One thing to note here is that for the derivation of xp, it's b that gets multiplied with x1. If we look at this picture here, b is the farthest component of the ratio from x1. So x1 gets multiplied by b, and similarly x2 gets multiplied by a. This makes sense because if you look at this picture, in this case b is larger than a. It means the point P is closer to x1. x1 should have more influence on P, so it gets multiplied by the larger component of the ratio. And following a similar derivation, we can find the formula for yp. It will have exactly the same form as xp. In the next section, we will use this section formula and also the angle bisector theorem to find the coordinates of the incenter. In this section, we're going to put together what we learned in the previous two sections to come up with a formula for the coordinates of the incenter. So again, we have triangle ABC. AX is an angle bisector. The coordinates of ABC are x1, y1, x2, y2, x3, y3 respectively. The side opposite vertex B is of length lowercase b. The side opposite vertex C is of length lowercase c. Lowercase b and c can be calculated from the coordinates of the vertices. For example, the length c will be square root of x2 minus x1 square plus y2 minus y1 square. In other words, all we need to know is the coordinates of the three vertices, and using those we can calculate the side lengths. So the first step is to find the coordinates of point x. Since AX is an angle bisector, it follows from the angle bisector theorem that the ratio BX to XC is C to B. So here I have marked BX to be of length CR and XC to be of length BR, such that the ratio is C to B. R can be any arbitrary multiplier. So using the section formula to find the x coordinate of x, which I am calling xp, the formula for xp is x2 times b, the further component of the ratio, plus x3 times c divided by b plus c. And the y coordinate yp has a similar form. The length of side BC is composed of CR and BR, and we designate that length lowercase a because it's opposite vertex A. So we get BR plus CR is equal to A, and we can use that to calculate R. So R is A divided by B plus C. So now that we know the coordinates of X, we'll use these and the coordinates of A to find the incenter. But first we need to know in what ratio does the incenter divide the length AX. So let's see how to figure that out. To find the incenter, first we're going to draw a second angle bisector from vertex B. The intersection point of this bisector with AX is the incenter I. Consider the highlighted triangle ABX. For this triangle, BI is an angle bisector and point I lies on the side AX. So we can use the angle bisector theorem on triangle ABX to find the ratio of the lengths of the segments AI and IX. This ratio will be given by the lengths of the sides of the triangle, sides AB and BX. The length of side AB is lowercase c, and the length of side BX is CR. AI to XI is given by C over CR. This ratio is 1 by R. Since we already know R, we can write this as B plus C divided by A. So now that we have figured out the ratio in which I divides the segment AX, we can apply the section formula to find the coordinates of I using the coordinates of the endpoints A and X. I divides AX in the ratio 1:R. Using the section formula, coordinate XI will be 1 times XP, the X coordinate of X, plus R times X1, the X coordinate of A, divided by 1 plus R. We already know all the terms in this formula, so let's substitute them. We know the formula for R. Let's calculate 1 plus R. It will be given by 1 plus A divided by B plus C, or A plus B plus C divided by B plus C. So now expanding Xi using all the known coordinates, we get 1 times XP, which is X2B plus X3C divided by B plus C, plus R times X1, which is A divided by B plus C times X1, and divided by 1 plus R, which is A plus B plus C divided by B plus C. Here B plus C is a common denominator in all the terms, so we can just cancel it out. What's left then is X2B plus X3C plus X1 times A divided by A plus B plus C. And rearranging that, we get Xi is A times X1 plus B times X2 plus C times X3 divided by A plus B plus C. And Yi will have the exact same form, so we will get A times Y1 plus B times Y2 plus C times Y3 divided by A plus B plus C. And of course, A, B and C can be determined from the coordinates as well, as we saw earlier. So just by knowing the coordinates of the 3 vertices, we can find the coordinates of the incenter.